What is Java Memory Model? Java Memory Model is a set of rules and guidelines which allows Java programs to behave deterministically across multiple memory architecture, CPU, and operating system. It is particularly important in a case of multithreading. Java Memory Model provides some guarantee on which changes made by one thread should be visible to others. One of them is the happens before relationship. This relationship defines several rules which allow programmers to anticipate and reason the behavior of concurrent Java programs. Let's look at what happens before relationship guarantees. Program order rule defines that each action in a thread happens before every action that comes later in a program order. This is known as program order rule. Monitor lock rule defines that unlocking a monitor lock happens before every subsequent lock on the same monitor lock. Volatile variable rule defines that a write to a volatile file happens before every subsequent read of the same field. Thread start rule. A call to a thread.start on a thread happens before any other thread detects that a thread has terminated either by successfully returned by thread join or thread is alive returning false. Thread interruption rule defines that a thread calling interrupt on another thread happens before the interrupted thread detects the interrupt either by having interrupted exception thrown or invoking interrupter or interrupted. The end of a constructor for an object happens before that starts of the finalizer for that object, known as finalizer rule. If A happens before B and B happens before C, then A happens before C, which means happen before guarantees transitivity. What is young generation? This is reserved for containing newly allocated objects. Young generation includes three parts: hidden memory and two survivor memory spaces, S1 and S2. Mostly of the newly created objects go to hidden space. When hidden space is filled with objects, minor GC is performed and all of the survivor objects are moved one of the survivor spaces. Minor GC is also checked for survivor object and move them to the other survivor space. So at a time, only one of the survivor spaces is always empty. Objects that are survived after many cycles of GC are moved to old generation memory space. Usually, it is done by setting a threshold for the age of young generation objects before they become eligible to promote to old generation. What is old generation? This is reserved for containing long-lived objects that could survive after many rounds of minor GC. When old gen is full, major GC, also known as old collection, is performed and it usually takes longer time. What is non-heap memory? This includes the permanent generation area which is replaced by metaspace since Java 8. PermGen stores per class structures such as runtime constant pool, field and metadata, and the code for methods and constructors, as well as interim strings. PermGen has been having replaced by metaspace due to the restrictions of its usage. The most important difference between the two is how they handle memory allocation. In the metaspace, the native memory region grows automatically. Hence, this helps us to get rid of the famous out-of-memory error caused by PermGen. On the other hand, because metaspace uses native memory, it is only limited with the operating system. So this means we can literally up all the memory on the server. Because this unlimited approach has its problems, we can add some new option like max metaspace size parameter to set the maximum metaspace of our application. PermGen versus metaspace. PermGen is available in Java 7 and previous version, whereas metaspace exists after Java 8 and newer versions. PermGen is a part of heap, whereas metaspace is a part of native memory. PermGen throws out of memory errors, whereas metaspace doesn't cause exception. Options for PermGen and PermGen max PermGen size, whereas we can only limit max metaspace for Java 8. What is cache memory? This includes code cache. Stored compiled code generated by JIT compiler, JVM internal structures, loaded profiler agent code, and data, and etc. When the code cache exceeds a threshold, it gets flushed, and objects are not relocated by the GC. Small and high-speed memory, most of the recently used items keep there, and it can be accessed by CPU for faster execution. Types of cache memory. L1 is the first level cache memory can work at the same speed as the CPU. L1 cache represents a small amount of memory it represents inside the CPU itself. For a quad-core CPU, every 4 quads have its own level 1 cache. L1 cache has two types. The first one is the instruction cache, which stores instructions required by the CPU. The second one is data cache, which stores the data required by the CPU. L2 is the second level cache memory. L2 CPU is outside of the CPU and it's connected with the CPU with a very high speed bus. L2 caches are slower than the L1. L3 is the third level cache. This is not present in the old processors. Some high-end processors may have this type of cache. It is located outside of the CPU and shared by all cores of the CPU. It is faster than RAM. When the CPU needs a data, it first looks inside the L1 cache. If it doesn't find anything, it looks inside to the L2 cache. If it doesn't find in the L2 cache, it looks into the L3 cache. If data is found in the cache memory, then it's known as a cache hit. If the data is found, then it is called a cache miss. How does a cache memory work with the CPU? When CPU needs the data, first of all, it looks inside the L1 cache. If it doesn't find anything in L1, it looks inside the L2 cache. If again, it doesn't find the data in the L2 cache, it looks into the L3 cache. If data is found in the cache memory, then it's known as a cache hit. On the contrary, if data is not found in the cache, it is called a cache miss. If data is not available in the cache memories, it looks inside the random access memory. If random access memory also does not have the data, then it will get that data from the hard disk drive. So when a computer is started for the first time or an application is opened for the first time, data is not available in the cache memory or in RAM. In this case, the CPU gets the data directly from the hard disk drive. Thereafter, when you start your computer and open your application, CPU can get the data from the cache memory or RAM. What special guarantees that the Java memory model holds the final fields of a class? JVM basically guarantees that the final fields of a class will be initialized before any thread gets hold of the object. Without this guarantee, a reference to an object may be published, become visible to another thread before all the fields of the object are initialized, due to reorderings or other optimizations. This causes racy access of these fields. This is why, when we are creating an immutable object, we should always make all its fields final, even if they are not accessible via getter methods. What is in-order execution? In order to develop a multi-threaded application, we need to understand in what order the actions are executed in the application and how does the sharing between threads. In the expected case, this is supposed to be flow by fetching the instruction, decoding the instruction which loads any required data from main memory among other things, executing the instruction, and write back the result which stores any generated result to main memory among other things. Out of order execution. When we write a program, we expect that those series of statements will be run in the same order that you have written it. But it's completely possible that a compiler or the JVM, all the CPU will change the order of your instructions to drive some performance out of it, and it's done in a way that the program semantics remain the same, so the program output will always remain the same, even though these changes are made by the compiler or the JVM or the CPU. What is the difference between stack and heap in Java? Stack memory is used only by one thread of execution, whereas heap is used all the parts of the application. Stack memory is used in parts, whereas shared resource whereas shared resources entire application use heap during runtime. In access perspective, stack memory cannot accessed by other threads, whereas in heap memory, objects are stored in the heap are globally accessible. In memory management perspective, stack memory follows LIFO manner to free memory, whereas heap is based on generation associated with each object. In lifetime perception, stack memory exists until the end of the execution of the thread, whereas heap memory lives from the start till the end of the application execution. In usage perception, stack memory only contains local primitive and reference variables to objects in heap space, whereas heap memory, whenever an object is created, it is always stored in the heap space. Stack memory uses only primitive variables and references to objects that are created in heap, whereas heap memory uses all newly created objects. In size perception, limited size depending upon US usually is smaller than heap, whereas heap memory usually user-defined or default, no size limit from OS. In order perspective, stack memory accessed only last in first out memory allocation, whereas heap memory accessed via complex memory management technique that include young generation, old generation, tenure generation, and permanent generation, and after Java it is metaspace. In life perception, stack memory exists as long as the current method is running, and heap memory exists as long as the application runs. In efficiency perspective, stack memory comparatively much faster to allocate when compared to heap, whereas heap memory is slower to allocate compared to stack. Allocation deallocation perspective, stack memory is automatically allocated and deallocated when a memory is called and returned respectively, whereas heap space is allocated when new objects are created and deallocated by garbage collector when they are no longer referenced.